So I will start by mentioning that this is based on a joint work with Roman Bezurbannikov, Andrei Ionov, and Yakov Warshawski, and you can look it up on arXiv. It has roughly the same title. So I will start first with algebraic motivation. Is it okay if I write here? Or is so let G be some split reductive group. Defined over a finite field F. And you can think for most of the talk for G being GLN. Let B inside G be a split Borel group. And I will fix some standard notation. U inside B will be a unipotent radical. And T inside B will be a maximal torus. So I will be interested in representations of G as a finite group. So question is to classify irreducible representations of the finite group G of Q. Over a field K of characteristic 0 algebraically closed. So there is this is in general a hard problem, but there are some representations that are more easily accessible. For example, there is a class of irreducible representations called the principal series representations. So these are, by definition, irreducible representations. Appearing inside the induction of the trivial representations of a Borel to the whole group. Or equivalently, you can say that these are irreducible representations that have a fixed vector with respect to the action of a Borel subgroup. And so, tautologically from this, set of irreducible principal series irreducible representations is in bijection with irreducible representations of the endomorphism algebra of this representation. So let me denote it by IB. And this endomorphism algebra has a nice description. As a Ivachori-Hecke algebra attached to the corresponding Weil group. So I will write it HGB. And so another description of it is that this is an algebra of functions on the double cosets with respect to the Borel subgroup. With product given by convolution. And again, so the upshot, almost tautological from this, is that number of elements in PS of T is the same as the dimension over K of the center of this Ilafori package. Okay, so this is a classification of the simplest reducible representations of a finite group of Lie type. Then, sometime in the 70s, Delini and Lustig defined that a certain class of representations, they called unipotent representations of G of FQ. So this is a certain class that contains principal series representations. In general, it is not equal to it, but well, for example, for G equals GLN, these two classes coincide. But yeah, in general, class of irreducible representations is bigger. So I will not give a definition of unipotent representation, so I can say briefly, for those who already know, that these are representations appearing in compactly supported cohomology of the Delini-Lustig varieties. So the main idea that I will be motivated by in this talk is that the number of this more general class of representations is a dimension now not of a center of some algebra, but a dimension of the K group of the categorical center of H of G, and this will be a category. So basically, the categorification of this upshot in the bottom should give us some classification of unipotent irreducible representation.
Excuse me, categorical center is Drinfeld center, right?
Well, this is a great question I will address later. Yeah, it's one of the main points of this talk. That what I will be talking about, I will use some modified. Okay, let me first say with what kind of categorifications I will work. So I will be categorifying.
Excuse me. So this idea is actually a theorem, right?
Yes, I will make
it's been known for quite some time.
Yes, in some setting.
Also using H for both the algebra and for the category.
Algebra will not appear anymore. So let me. Yeah, I will say H algebra. That's. And this notation is preliminary. But I will say what I mean by Hecke category in more detail later. So I will be interested in the categorification of this description of the Hecke algebra as functions on the double cosets. So the standard categorifications of function on some variety defined over the finite field is a category, a time-derived category of sheaves on it. So I will work with this and with other sheaf theoretic setup. So let me. So let X be some stat. So the stacks I will work with will always be of the form y divided by h, where y is some scheme, and h is a group, algebraic group. And so this stack can be defined either over a finite field, algebraic closure of a finite field, or, for example, over complex numbers. And to this stack, we will attach a category d of x that can mean several different things. So in general, this will be some derived category of sheaves on x of some constructible flavor. So examples that you can consider, and the whole point of my talk is that the argument I will talk about should work in all these examples. So you can take x defined as a finite field and take d of x to be Deligne's mixed étal category of x with coefficients in QL bar. So this is mixed quadratic category. So another example can be if x is defined over C, d of x will be derived category of holonomic D modules. So derived category of D modules with holonomic cohomology. Well, sorry?
You want regular?
Do I want what?
Regular holonomic?
No, I will say not just holonomic. I mean, yeah, if I wanted regular, I would equivalently, again, be x over c, and d of x will be constructible, algebraically constructible derived category of x considered as an analytic topology. So these are some examples for which our setup works.
So in the third case, what kind of coefficients do you want to?
Yeah, that's a great question. So I can consider coefficients of characteristic 0 or large enough modular coefficients, but it's really large, greater than order of the Weil group. You will see what exactly I mean. Okay, so what all these examples have in common? So these are triangulated categories. And what they all satisfy is some form of six-functor formalism. So what do I mean by this? I don't want to spell out the axiomatic definition of six-functor formalism, but what I will want is that for each map f of xy, each reasonable map, I will have a collection of functors So two functors that go in the opposite direction, and two functors that go in the same direction. And also some duality on G of x. And external tensor product. So this is what these six functors with various compatibilities between them is what is usually referred to as six-functor formalism. And by compatibilities, for example, what I will mean is a base change isomorph. Okay, is there any questions about this? Okay, so now I'm ready to say what the Hecke category is.
Can you lift everything to some DG category? Like,
Huh?
with DG categories instead? DG.
Well, I can't. But there are people, I will mention the known results, and some of them are in the world. In fact, we work with them in some form, but not in the most general state. So now, definition, the Hecke category. Or let me say equivariant. Will be just shifts on double quotient. And then we will be interested in some form of categorical center of this, or of some similar category. And in what sense is it related to the any sort of representations? Is the following thing. So first we study not the representations themselves, but characters. And characters are functions on the adjoint quotient of G by itself. So we consider the adjoint quotient of G by itself, and consider the following diagram. So we have two maps, which are just projections. So B is diagonally embedded in P cross G, or just into G, and we have a corresponding projection on the quotient stack. And so definition due to Lustig is the following thing. So character shift on G G is an irreducible perverse shift appearing in perverse cohomology of pull-push of some shifts in the Hecke category. So where L is, say, a simple Paris sheaf. So in the name, character sheaf is that this gadget is supposed to categorize the characters of, say, reducible representations of the finite groups of data.
Can you make precise what you mean by appearing in?
So yeah, sure. So these are, the map Q is smooth, and this map is proper. So pull-push will be a semi-simple Paris sheaf.
So that's so in your settings that's in the second setting, but in the other settings you will.
Yeah, this is good point. So when I don't have a decomposition theorem in this generality, I will use a different definition. Yes, I will say yeah. Yeah. So this was a question about modular coefficients, or yeah. Okay, so the category 5 statement that we want is the following. So the, again, slogan, which can be made precise in multiple different ways, is that category of character sheaves is a categorical center of D G mod B mod B. And so what are the known results?
So you need to take some additive closure or something like this?
You mean, yeah. So this I defined what simple Paris sheaves are, simple character sheaves are. What I can now take, I can take a full subcategory of D G mod G, whose cohomology have filtration with simple quotient. The simple Paris sheaves. So yeah, I can take the triangulated closure inside DG mod.
So the empirical this thing on this board will be triangulated.
Not always, sir. Not always. I will say all the results. Yeah, it's.
Just, can I just just for people who are not in this area, so when you start with a simple Paris sheaves on D, G mod B,
Yeah.
so there are only finitely many of them.
Yes.
They correspond to elements of the while group.
Yes.
And on the other side, you'll only have finitely many
Yes.
objects
Only finitely many classes of simple objects. Yes.
on the left.
Yes. Yeah. So let me spell this out. Sorry about that. So let me write for the derived category of character sheets. Which I will denote DCS of G. So what is this? This is a full subcategory, triangulated subcategory. Of derived category G. Such that, consisting of objects whose Paris cohomology have simple have a simple constituents simple character sheaves. So as was mentioned, here there is only a finite number of simple objects, and so there is a finite number of different simple pair of sheaves, but there can be some non-trivial extensions of that.
Just to get a feeling, so when G is GLN,
Yes,
the size of the Grothendieck group of this category
is the same as size of representations of SN.
the number of partitions.
Number of partitions. Yeah, so this is precise. Number of partitions should be thought as the size of principal series. So for GLN, principal series is the same, but in general, this category will categorize the unipod. Okay, so let me state some known results. So the reason I was so vague about the details of what Hecke category is and what character sheaves are is that there are certain technical complications of setting the whole picture so that this statement about the categorical center holds. So now the results are as follows. So there is a result of Bezrukavnikov Hinkelberg and Ostrich. So for them, character sheaves is a abelian category of D modules on G. So these are D modules, abelian category of D modules whose simple constituents appear as in this pull-push diagram. And the Hecke category is a abelian monodromic variant of the Hecke category realized as D modules. And then for them, center, categorical center is just a Drinfeld center. So this is one result. Another result is by Nadler and Ben-Svi. So for them, D of X will be infinity category of D modules. So this is not a triangulated setting. This is a large category. But then the advantage of this is that you have a notion of a center in the infinity categorical setup. You have notion of trace, which is a Hochschild cohomology of your category, and in this case, center and trace coincide. And so they prove that this infinity categorical variant of this category. So, is categorical center of the sheaves. So, I'll write this. But again, this is in the setup of infinity categories of D modules. And then in the similar vein, Mm. There is a more recent result by Ho and Lee. So this is also similar infinity categorical setup, but this d of x is infinity category of L-adic sheaves. And actually their setup works more in a more general setting. So this is how they formulate it, but it is expected that their work also is applicable wherever you can define a nicely behaved infinity category of sheaves on X. And so there is another family of results.
With X?
Huh?
With X?
A stack, quotient stack.
One
So-
of those guys.
Huh?
One of those guys.
Yes. I mean, they need more. They need products of those guys, stuff like that, but of stack of this kind. Yeah?
In the first example, is the equivalent to a category of, is it abelian in the first example? Z?
This in, so yes, these are about abelian categories.
Because Z is abelian, and
Yes. So this is Drinfeld center of this abelian Hecke category.
it's also
It's
abelian,
also abelian.
and the homes are finite dimensional.
The homes are finite dimensional. Yeah, and so there is another family of results by Lustig. So he also works with in L-adic setting, but for him he considers asymptotic versions. I don't want to. So in this case, these are semi-simple categories. So there is a way you can take a associated gradient of this category so that everything becomes semi-simple, and then Lustig has a similar result for a Drinfeld center of a semi-simplified categories. Okay, so from this list, yeah, you can see the difficulty. So one approach is to somehow reduce to abelian categories, which is weakening the result. Another way is to consider big infinity categories, which is probably a correct approach to defining Drinfeld center, but it comes with its own technical complications. And the last approach, it uses some very specific things about the Hecke category that you can actually consider this asymptotic semi-simplified version. So the aim of this project is to prove the result for triangulated d of x working in general setup. So the proofs should be applicable to all the shift theoretic setups uniform. And so to give a main idea, let me first spell out what is the difficulty in a simplified setting. So let's see be a triangulated monoidal category, where monoidal structure respects the triangulated structure. Then Drinfeld center of C is not a priori triangulated. Well, this is a very standard problem in the theory of triangulated categories, that columns are not functorial. So the additional structures that you have on your categories don't usually produce triangulated categories.
So can you remind what exactly we want to get? So what the result should be? You raised the slogan, so.
Yeah, so the slogan is here. So the derived category of character sheaves is a categorical center of the Hecke category.
Okay.
And the problem is to find the right formulation. So this is what this works. So another example of this, more general, I guess, is that, so again, let C be triangulated. And T acting on C is any monad. Well, exact monad respecting the triangulated structure. Then the category of modules is not a priori. So this is a similar problem in a more simple setup. However, it turns out that for some very special monads, this is the case. So what I will be interested in particular kinds of monads. I mean, from the adjunctions. So let C and D be two categories with a pair of factors between them, F and G. I will assume that G is left adjoint to F. Then the composition is a monad on D. So Balmer gave the following theorem. So first definition. T equals to Fg is separable if the co-unit map from GF to identity splits. So there is a natural transformation in other direction such that the composition is an isomorph. And so we have the following theorem.
Composition in which direction?
So identity is a summand of G. So the theorem due to Balmer is that if T is separable, then the category of T modules on D is triangulated. And triangulated structure is just characterized by the fact that forgetful functor is triangulated. And so the corollary of this. So I should mention, so this I sweep some of the generalization under the rug. So for Balmer, separable is something slightly more general. So he defines what a separable monad is in general. In general, this is just that the multiplication splits as a bimodule map, just in algebra. But this is all I will need. Yeah, and so corollary of this is the following simple thing. So if C and D are again as before, and I assume they're idempotent complete, then C is actually equivalent to the category of T modules in D. So this is some form of Barbach's theorem, which is simpler in this case. It's much simpler to prove.
And F and G are these push-pull things, right?
They will be, yeah, yes, they will be right now, yeah. So yeah, let's go to this.
So here C and D are supposed to be triangulated?
Yes.
Yes. And the factors F and G to be exact?
Exactly, yes. Yeah, so recall that we had the following diagram. And so we have two functors. One is called the character functor, which we encountered before. And we have a functor that is adjoint to it, which is called the Harishchandra functor. Which is just going in the other direction. So this Harishchandra functor is monoidal functor. And this is supposed to be our embedding of the center to the category. So for the expert, I'm sweeping some shift under the rug. So I use that one of the maps is smooth. And another is proper. Huh?
Bijointness here or not? Is there a bijointness up to a shift or not?
No.
So this is not bijoint.
No. This is, yeah, this is. Now the problem is that the map that's the direction. So the map this map is not split. And this is, I claim, basically the reason of all the infinity categorical problems that arise. So this monad is not separate. However, one can consider a mild modification of this diagram. Which is the following. So we take, again, G. But instead of averaging with respect to the Borel subgroup, we are averaging with respect to the unipotent radix. So what we are landing on is the following stack. So we are averaging with respect to unipotent subgroup. So since this was adjoint equivariant, we get double quotient. by the unipotent radical, but also we have this adjoint action of T left over from before. So let me introduce the same notation, P and Q, and the same notation for as before. So now claim. This, I believe, was first noticed by Ginzburg. If you go along Harishchandra map and then along the character map in this setup, that this functor is isomorphic to the convolution with the Springer sheaf. So let me recall what this is. Springer sheaf is, you consider the variety n tilde called the Springer resolution. So these are pairs G x B inside the product of G and the flag variety such that well, G preserves the corresponding flag. So X inverse GX is in B. In U. So G is supposed to be unipotent and preserves the corresponding flag. And so the Springer sheaf is pushed forward under the natural map of the constant sheaf on n tilde, where the projection is from n tilde to G. This just forgets the flag. And so now this is a well-known and important fact in geometric representation theory that in many sheaf-theoretic setups, Springer sheaf is semi-simple. Or what we need is actually slightly less, is that, so theorem, which is classical, is that the Springer sheaf contains as a direct summand the sheaf I will call delta E. So this is just a delta sheaf at the unit in G. And so it follows that this functor contains as a direct summand convolution with delta sheaf, which is just an identity functor. So this is why we need a restrictional characteristic in modular case, because in modular case and small characteristics, this will not be true.
What does that notation mean? With the inclusion, with the direct sum?
Yeah, so it contains as a direct summand.
Okay.
So this. Okay, are there any questions about this? Okay. So now, as a corollary, let me write it here.
You also have it in modular case, right?
Huh?
In the modular case, you also have this.
In the modular case, again, I have this, but only if the characteristic is pretty large.
So you do have the separability, or
Yes,
you do
yes,
have
this is the point. Sorry, yeah. So yeah, let me write it here. That this the monad HC CH is separable. And the derived category of G is equivalent to the category of modules over this monad in Hecke category. Sorry, in this case, I call the Hecke category the category of the stack.
And here you don't have any restriction on the reverse cohomology of
Yeah, so far no. Yeah. So I should say yes. Our result will be more general, and then can be specialized to character sheet. Okay, so this is a type of Hecke category I will work with. So now, since we modified the notion of the Hecke category, we actually need to modify a notion of the center a little bit. So again, let me denote by H1 is the following category. So this category. And let me define H2 to be almost a square of this category. So for this, I take G mod U plus G mod U divided by T squared. But T squared acts in a twisted way. So this is a product of the torus acting along the first and the fourth coordinate times the torus acting along the second and third coordinate. And so first let me say a sign. So if A is just a unital algebra, you can say that center of this unital algebra is an endomorphism as A bimodules of A itself. And so this is how, for example, the infinity categorical center can be defined as endomorphism of the Hecke category over its square. So yeah, this aside is for the purpose of now explaining where the next theorem comes from. So this is our main result. Is that D and G are endofunctors over H2 of H1. So the point is that H1 is H2 module. So this is the main statement. And again, as was mentioned, character shifts don't appear. So this is a more general statement that as corollary.
And here, on the functors, you mean triangulated endofunctors?
Triangulated endofunctors commuting with action of H2, but everything in a one categorical sense. So like as you would define in a one categorical sense what it means to commute with action. Okay, and so the corollary we recover that the derived category of character shifts on G is a certain is a certain subcategory of antifunctors of the monodromic version of H2 and H1. So I don't think I have time to go into detail, but this is stands for monodromic. And as another corollary, we so this can be also done for general monodromy. I only discuss the unipotent character shifts, but there is a notion of a character shift of generalized monodromy. And this can also be deduced from this non-monodromic result. And finally, as a corollary, we deduce a abelian statement. Of Bezrobotnikov, Finkelberg, Ostrich by considering explicit DG models. For H1. And as a final remark, so this category, I just want as a motivation for this particular conference, says that this category is nice in the sense that this H1 monodromic is the host of Y5 Khovanov-Rozansky homology. So this is the category where you can compute Y5 Khovanov-Rozansky homology. So this is like not a completely accidental category. Okay, yeah, I think I'm out of time. Thank you very much.
So in the Drinfeld Center, you also have to choose the braiding. So this is part of this construction.
You mean here? Yeah. So part of the data of what is endofunctor as a module category will be how the functor commutes with action. Mm-hmm. So this is your an analog of braiding here.
And like the statement would be that this is like, if I have an object, so by your separability thing, you're saying that you can actually like embed your D of G model joint in the original category. Like this would be like.
So So this is a good question. So this category is not braided a priori. There is some analog of braiding, but this is not a braided monoidal category a priori. So you see that this is braided from here, from this equivalence.
No, I think I'm asking, so like by your previous like separability, like by this corollary on the bottom.
Yes.
You're saying that actually your D of G mod G will be this monad equivariant things inside like G mod B mod, whatever, G mod U mod U.
Yes.
So in particular, like if you have an object there, you're saying like a unique way to choose it.
Yes, exactly. Yeah, sorry, I didn't have time to talk about the proof. Yeah, so the proof uses this. This is not all the structures as you need, but it is easy to show that there is a functor from here to here. So the point of this description is that it's easy to show that there is a functor from endofunctors to the modules. This was complicated previously because it's not clear how to show that there is a functor from a categorical construction of Drinfeld center to some shifts on G mod G.
For link homology, do you use the algebra version or the group version?
Group version.
Group version?
Yes.
Then the variables will be invertible?
No, so yeah. In this sense, I work with Zirkel bimodules. And so the variables are Chern classes of B, of BB. This is not invertible. And here another variable will be unipotent monodromy. You need to complete so that logarithm will not be invertible. Logarithm of monodromy. So this is non-invertible situation.
And continuing on Eugene's question, so does this construction actually helps you to write braiding between two objects? You're taking like two objects from this, category, and I just want to. I know that products in two directions are the same, but there is some kind of something.
No, I
braiding.
yes, I don't think so. All the constructions of braiding, I know they somehow come from this description, from G mod at G. It's not easy, so the only way I know how to write braiding here is to relate it to G mod at G.
The principle it should be that, right? It's saying you have an underfunctor.
Yes.
You're commuting with an action from two sides.
Yeah. No.
You can act not on the thing in the middle, but on either side.
Yes.
And
exactly. No. The point is you do have this module. Module data of the module and the functor. The problem, I guess, that and I don't know how to make it precise, but H2 is not a square of H1. So there is.
Sorry, that's the issue.
Yeah. So there is some object in H2 that doesn't come as a product of two objects.
Is there some relative version of this construction where instead of purifying the center of the Hecke algebra, or you just look at some kind of relative version where you're purifying some invariants under the action of a subalgebra, Hecke subalgebra, like invariance of S2 instead of invariance of entire Sn?
You mean like categorize the centralizer of Hn minus 1 and Hn?
Yes, or even like H2 in H2.
So I don't. So first, I think that the same argument works if you replace B by the parabolic, and for the if you write the parabolic version of these spaces. So this is one way to get the relative version. Yes, I would be very interested. Yeah, if for example, Justice-Murphy braid can be obtained in this abstract categorical sense, as a centralizer of Hn minus 1 and Hn, but I don't know the precise name.
I was kind of thinking that if you have a separability, then you can do one side of the Bernstein trace morphisms, and with parabolics you can do many of them. So there's trace morphism, and then you have bijointness, but here separability gives you just morphism in one direction, not in both directions.
Yes.
But maybe with parabolics you can do many of these morphisms.
Yeah,
that could be some interesting.
Yeah, it's interesting. I don't know. It was very interesting. Yeah.
Maybe related to Mike's question, is there some additional structure that you get when you consider parabolic induction?
So what to say? Yeah, so parabolic induction, it goes not with the Hecke not within the Hecke category, but to the category and the torus. So you can play the same game there. I don't think there will be much more you can say. So, for example, I think it's not. Yeah, it's a very complicated question if this component is split. I think for character shifts it is definitely not split. The monads that you get from parabolic induction and restriction, it is not split if you consider all sheaves on a torus. But I believe, although I don't think there is, I believe that this is true. It is split if you consider only character shifts. So there is a work of Lee about formality of the parabolic restriction and induction. I think it follows from that it is split for character shifts. But what you get is some sort of this formality result that lead us. But there are some other interesting games you can play, which are important from other point of view. Is, for example, you can say, okay, I'm interested in shifts for whose Harishchandra map, embedding of the center, is the same as parabolic restriction. So they have some a lot of vanishing, and then this picture is useful. Yes?
I would be curious how this H about 1 sort of can be interpreted by modules. I mean,
yeah. So the idea is that this is what I refer to when I'm saying about DG modules. So the idea is that you consider, well, this is, I guess you can do it in different ways, but this is how I like to do it. So you can consider the monodromic version of the Hecke category. So you consider shifts on G mod U, which are smooth along the projection to G mod B. So then your bimodules come from the logarithms of monodromy acting on the left and on the right. And then to come to H1, you say, I want to say that right monodromy is the same as left monodromy. The action, and there is like a homotopic coherent way to say it. You say, I add one variable of degree 1, and I say that its differential is the difference between left monodromy and right monodromy. So in this way, you obtain a DG model for monodromic version of H1. These are complex of Zergel bimodules with the action of some additional DG algebra that says that the left monodromy is equal to the right monodromy.
Can you see H2 in the same way?
Yes. Yeah, H2 is just some variant of, you consider the square of the monodromic Hecke category, and now you say I say that first monodromy is equal to the fourth monodromy, and second monodromy is equal to the third. So I just have two variables of degree 1, and I kill the difference along the first and fourth, the second and third.
Should I think of it as like two braids next to each other?
Huh?
So a braid here and braid here. Well, let's come in.
Yeah, this is don't have that much imagination. Yeah.
So if there are no further questions, let us thank